Okay, here we are for week 2. We're going to start getting into material behavior. But before we can talk about that, we have to talk about what happens inside things where the forces are actually moving around. We know that we could do a partial free body diagram and draw a placeholder because we know there must be some internal forces that allow the load that's applied over here to get to the reaction that's over here. So something's happening in that member, and we know we could figure out what that load would be. But now we need to make sure that we have members there that are strong enough to take those forces. And so to do that, we have to understand how those forces act inside the material. So to talk about that, we're going to start introducing the concept of stress and strain and how they're related to each other. So we're moving on to the other side of the equation now, but we're still not going to do much with that other side of the equation, or the reduced capacity side. But this is starting to let us talk about it. So today's lecture, we're going to just remind ourselves about the different forces, because we've talked about those a lot. And then I'm going to introduce the concept of stress and strain, and how they're related, and what a material looks like as you load it and unload it. What happens inside a material? How do we measure those forces happening in the material? And because we're engineers and we like something visual to look at, we draw diagrams of what's happening in there. And you saw a hint of that last week and in last semester's term, where we drew something called a force displacement diagram or a stress strain diagram. And we're going to talk about those and what information we can extract about a material from a stress strain curve. So we've looked at this a bunch, and in fact we've even analyzed these internal loads within an object. We've looked at axial forces, so compression, which is squashing, and tension, which is stretching. I'll get out my handy foam block. So compression, which is squashing, tension, which is stretching. These are all the strength or the life safety things. We have shear, which is what's happening along a single plane. When we try to move one side up, now this isn't stiff enough to be able to do it, it actually squashes. But as we try to shift two planes past each other. And we have bending, when as we apply that load, one side goes into tension and one side goes into compression. And depending what way we apply the load, which side's in tension and which side is in compression can vary. And then the last one that we don't really work with in this course is torsion, or the twisting of the object, which is kind of a funny little combination of moment and shear. So those forces are all the things that we want to talk about. We want to talk about how they move within the material. So now I'm going to introduce the concept of stress and strain. So stress and strain are to a material what force and deflection are to the object. They are the effects on the material of an object subjected to applied loads. So stress is similar to force, and strain is similar to deflection. But instead of talking about the object, we're talking about a small little piece of the material. So if we were talking about compression on this foam block, instead of talking about the axial load on it, we're talking about what happens over one of these little squares. So obviously, we're going to talk about axial forces first, because they're a little bit easier to understand. They just go straight. Compression's going in one end and going down to a reaction at the other. We know bending is part tension, part compression, and then something with nothing in the middle. So let's start with axial forces, because it's a little bit easier to wrap our heads around. So we have an object, our object, and we apply a force. Stress is what we're saying is happening to one unit area of that material. So they're related to each other. So this stress is dependent on what this force is. But we talk about it over one little element of the material. And I'll explain why we do that in a few slides. Strain and deformation are very similar. If we have some unknown applied force, our object deforms some. Well, our unit object within this is also deforming in a related manner. So our stress is related to our force, and our strain is related to our deflection. So see, we had some sort of deflection or deformation here. So we'll start with stress. And we've kind of talked about stress a little bit when we talked about footings last term. It's the same idea. Stress is defined as the force per unit area. So instead of talking about the force over one object where we have to know exactly what the size of the object is, we're going to talk about that force spread over the area and what it relates to in every little unit portion of the area. So stress is measured in newtons per millimeter squared, or MPa. So not kPa, like we were talking about our applied loads last term, like our live loads tended to be in 1.9 to 4.8 kPa. We're talking about MPa now. So newtons per millimeter squared. So instead of kilonewtons per meter squared, we're talking about newtons per millimeter squared. So that means our force needs to be in newtons, not kilonewtons. So if we have a force that's in kilonewtons, we have to multiply it by 1,000 to talk about it in newtons. And that means that our cross-sectional area is in millimeters squared. So we'll need to be able to make those conversions back and forth very easily too. So let me just show you what I'm talking about. If we have a force over some blob of an area, our stress is that force spread evenly over that area. If we have the same force over half of the area, do you think the stress is higher or lower? We have the same force but half the area. Does the stress increase or decrease? Intuitively, if you've ever, walked on snow, you know that the bigger the area for the same load, the lower the stress. So if we've made our area smaller, our stress must be increasing. We have the same force over half the area, or 2PA instead of PA. This is our stress, and this is twice the stress. Let's take a look at another one. We have our force over our area, or P divided by A for stress. If we took half the force over half the area, what do we think? Does the stress go up or down? We have half P divided by half area, or P divided by A. The stress is the same on both of these. And that's why this is really handy. All of a sudden, we can talk about the material almost independently of the things that are happening around it. We can take the big thing, break it down, talk about it very easily, and then go back to talking about the big thing. And that's important because buildings and these objects we're talking about are massive. We need to be able to understand the material on a small scale. How do we test things? Do we actually go test big buildings every time we need to figure out this stuff? No, we can talk about it by testing small objects, understanding how it works, and then extrapolating back out to the big object. So I'm going to do a calculation now. Okay, we have me going out, walking around outside, and I want to know what stress my feet exert on the ground. I'm wearing my Blundstones that day, and I know I weigh about 600 newtons, and my area of my Blundstones, which I've measured, is 240 millimeters long by about 3 inches wide or 75 millimeters wide. And I want to know what stress that is on the ground. So let's take a look here. We have Shannon in her Blundstones. We have a force equals 600 newtons. The area is 240 by 75, and I've got 2 feet. So we can calculate this. We've got 240 times 75 times 2, or 36,000 millimeters squared. We know that stress equals force divided by area, or 600 newtons divided by 36,000 millimeters squared. 600 divided by 36,000 equals 0.0167 MPa. Newtons per millimeter squared is MPa. So Shannon, standing in her Blundstones on the ground, exerts 0.0167 MPa of stress on the ground. Let's take a look at me feeling fancy. I go into my closet and I bring out my fancy high heel shoes. I'm going to assume that all of the weight is on my toes, that I'm standing on my toes because I don't want my heels to go down into the ground. As anyone who has ever worn high heels in grass knows, the heels tend to go down into the grass. And so we'll try to walk on the front part of our toes to try to imagine that, or to manage that. So I've measured my high heels, and they are 4 inches by 75 millimeters. What do you think? Is my stress going to be higher or lower in my high heels? The front part of my heels on the ground. What do we think? Well, we've got Shannon heels. So the force hasn't changed. So the same force, but the area is now 100 times 75 times 2, or 100 times 75 times 2 is only 15,000 millimeters squared. So what do you think? Same force, smaller area. Is the stress going to go up or down? I think our stress is going to go up. Stress equals force divided by area. We have 600 newtons divided by 15,000 millimeters squared. 600 divided by 15,000 is 0.04 MPa. Our stress did in fact go up. Shannon putting on smaller shoes increased the stress. So it was the same load over a smaller area, means we have an increased stress. Now, I'm worried about the amount of stress I'm putting on the ground because I'm trying to walk across the snow. So I go and I bring out my trusty snowshoes. And these I've measured to be 1 meter long by 150 millimeters wide. And I have my 2 feet. So let's check this now with Shannon and snowshoes. Again, intuitively, everything you need to know about structural engineering you already know. I think you intuitively know that the stress is going to go down. It's why we wear the snowshoes. We are trying to spread the same force over a bigger area to lower the stress we put on the snow. So we have the same force, but our area now is 1,000 by 150 by 2. So 1,000 by 150 by 2 is 300,000 millimeters squared, or our stress equals 600 newtons divided by 300,000 millimeters squared. 600 divided by 300,000 millimeters squared, or 0.002 MPa. A much lower stress than either of these things. So taking that same force and spreading it over a bigger area decreases the stress. And if we knew how much stress the snow could take before it failed, we would know if I could walk across the snow. If snow could take up to 0.001, or let's say our snow could take 0.01 MPa. So snow, I'm making this up on the fly, max equals 0.01 MPa. Blundstones, which were 0.0167, well, that's greater than that. No. Heels, 0.04 is certainly greater than that. It doesn't look like the heels could do it. The snowshoes, 0.002. The load is much less than the capacity. It looks like the snowshoes could walk on that snow. I think we had two. There's another example right in a row here. So, what is the stress an elephant exerts on the floor if it weighs 44 kilonewtons and its feet are approximately 500 millimeters in diameter? So we've got an elephant. Let's see if I can draw an elephant. There's a reason I am not in architecture by any means. I don't know why I'm doing this. Well, it looks more like he's got lion feet. Okay. There is our elephant with 4 feet. Oh, let's make this bigger. You guys can't even see my beautiful elephant. What a waste on the world. Okay, here is my fantastic elephant. He's a happy elephant. Each one of these is 500 millimeters in diameter. And we know that this elephant weighs 44 kilonewtons. Yes, I did research on what an average elephant weighs. So we have a force of 44 kilonewtons. Now, when we were talking about our overall objects, we like to keep things in kilonewtons. It's very, very handy. But the second we start talking about stress, we like to talk about it in newtons. I know it's a pain in the butt that we switch around so much, but it does start to be very handy, and it does start to give us numbers that we can work with somewhat easily. So trust me when I say, as soon as we're talking about stress, we want to convert this to newtons. So it's 44,000 newtons. These two things are equal. It's just handy to start talking about it in newtons now. Our area is 4 feet times pi r squared. Or 4 times, I'm going to cheat and just do 3.14 times 500 divided by 2 to get our radius squared. All right, 4 times 3.14 times 500 divided by 2 squared. Oh, it looks like in the past I've actually plugged in the final, the calculation I did in here, I actually plugged in pi. Let's see what happens if I actually make this pi. Yeah. So you can do either. I'd try to build in that rounding error, no problem. 785,398 millimeters squared is the total area of our elephant feet. So stress is force divided by area, or 44,000 newtons divided by 785,398 millimeters squared. Plug that into my calculator, and I get 0.0560 MPa. Wait a second. Shannon in heels, pretty darn close to that. I'm feeling very insulted that this seems to imply that I exert the same force as an elephant. But this is why it's important to be talking about stress. We're not talking about, it allows us to talk about it in a broken down manner that we can relate to the material. If you notice, it was a bigger elephant with bigger feet versus a lighter Shannon on smaller feet. It does not mean I weigh the same amount as an elephant, which I hope is pretty obvious. Let's try looking at this. Let's say that pesky elephant went into my closet and picked out 2 pairs of heels of mine. So we go in and we want to see what happens when that elephant wears my shoes. So we have, let's draw him in fantastic heels. And we're going to assume he has the ability to walk on his tippy toes in those heels, the same way I did. So we have 44 kilonewtons, or 44,000 newtons. The area now is 4 times 100 by 75, because he has 4 feet and I only had 2. 4 times 100 by 75 equals 30,000 millimeters squared. So the elephant in heels is going to be 44,000 divided by 30,000 millimeters squared, and we get a stress of 1.47 MPa. It makes sense that that elephant wearing the same shoes I was would have a much higher stress on the ground. So these were ones to just help us get our head around what we're talking about. So here that is here. What if we started talking about actual materials that we care about? What if we had a blob of steel that we're going to use to just help us talk about here, and this blob of steel is 25 millimeters by 25 millimeters by 25 millimeters. And we know that this steel can see we know that it has the ability to take, kind of spread out everywhere over it. Oh, sorry guys, a maximum stress. They've told us that the max stress this can take is 350 MPa. We want to know what force that equates to. What's the maximum force that this 25 by 25 by 25 piece of steel can support? Well, we know that stress equals force divided by area. We want to know a force now. So force equals stress times area. We already know that the stress is 350 MPa, or the maximum stress that it can take is 350 MPa. That's what they told us. And the area that it's spread over is 25 millimeters by 25 millimeters. 25 by 25, let's plug that in. 625 millimeters squared. So the maximum force is 350 MPa times 625. So 350 times 625 is 218,750. And now this is where it's important to remember what your units were. This was newtons per millimeter squared, and this was millimeters squared, meaning this is newtons. This is an answer in newtons. And this is now why it's handy to be able to convert back into kilonewtons. When we're dealing with the stress, we like to work with it in newtons. But when we're talking about the force either at the beginning or at the end, we like to talk about it in kilonewtons. So we'll divide it by 1,000. We have 218.75 kilonewtons. So this 1 inch by 1 inch blob of steel, if the maximum stress it can see is 350 MPa, that's it. Beyond that, the blob disintegrates. We don't know. That's just the maximum it could possibly see. That means that that particular blob of steel could see 218.75 kilonewtons. What if it was 50 by 50? Well, it seems like there would be 4 of these. The stress would stay the same. We'd have 4 times the area for the same stress. So 4 times the force could be exerted on that blob all of a sudden. So that is worked out here for you, that calculation. Okay, now that we've talked about stress and done a few examples on stress, let's switch to strain. Now, strain is the one that's related to deformation, and it's a little bit harder for people to get their head around. We don't have, or people think they don't understand the practical examples of strain. And I'm going to be honest, I struggled to try to find a practical example to talk about. But you do intuitively understand strain. It's a word you've used. And if we stop to think about it, as I've said with everything throughout the structures curriculum, that you know everything you need to know about structures already. So strain is the relative axial deformation of an element subjected to axial load. The object moves, the element moves, and it's as simple as that. So strain is the relationship of the change in length to the original length, or strain is delta L divided by L. This symbol, this Greek symbol, is delta, and it almost always represents change. So the change in length divided by the original length. So I've written here LA is the length after applied load. So delta L is the length after the load's been applied minus the original length. And that delta divided by the original length is strain. So how much has it moved compared to how big it originally was? That means we're dividing millimeters by millimeters. So technically strain is unitless. So it doesn't matter what units you're talking about, your strain remains the same, as long as you're calculating it in the same units. So if this was inches divided by inches, it would be the exact same strain as if it was millimeters divided by millimeters, or meters divided by meters. Why are we talking about it in millimeters? Well, we're going to see a relationship between strain and stress that allows us to basically expand these equations a little bit. So I'm going to strongly recommend that when we're doing calculations to convert it to millimeters, just so that we're consistent. I find it handy too, sometimes, to always write millimeters per millimeters, just so that I remember what's going on with my strain. You don't have to. If you're really good at holding that info in your head, no problem at all. But writing millimeters per millimeters, understanding that that means it's unitless, might come in handy when we move on to looking at some of the more complex equations where we combine stress and strain. So strain is the change in length divided by the original length. That can be a little bit hard for people to get their head around sometimes. So let me show you some physical examples here. We have an original object with the length L, and we apply a force. What the force is doesn't matter. What we care about is how much it moves. So we have some change in length. That's our new length. That was our original length. So that is our change in length. So delta L divided by L. If we have an object that is half the length, but it moves the same amount, so the delta L stays the same, do we think there is more or less strain? We had half the original length, but we have the same change in length. So delta L divided by half L, this is strain, and this experiences twice the strain. It deformed twice as much. Even though that was a bad way to word that. The amount it changed was the exact same, but we're talking about strain, which is how much does it move, or basically how easily does it move. And this moves twice as easily because half the length moved the same amount. So we're saying it moves twice as easily. So let's look at the same original length, the same delta. So delta L divided by L is our strain. We have half the original length, but now we've only deformed half the delta. So we have half the delta divided by half the length. Our strain is the same. So we can see that these two things experience the same strain, or they take the same amount of effort to deform, or they deform at the same ratio. So I'm going to show you an example that's maybe a little bit easier to get your head around with no numbers, okay? Hey Dave, why don't you just come say hello to everyone?
You gonna put some strain on me?
I am going to put some strain on you. So you just have to say hi, because I find embarrassing you quite fun. You can go sit down. Okay. That's all we needed of me. So here's a fantastic picture of Dave rocking a fantastic mustache one time. And so it's the summer. Dave's been doing a lot of barefoot water skiing, enjoying himself, chopping down trees, very outdoorsy, very in shape. And he puts on his shorts. And they fit perfectly. They're just the perfect fit. Fall comes, we've been inside a bit more, you know, we've been drinking some beer, eating lots of good food, sitting around the fire, and he's put on a few pounds. And he goes to put those same shorts on. He's stretching the elastic band just a little bit. Then the holidays hit. We eat a lot of turkey, we drink wine, we eat cookies, all the gingerbread you can imagine. And he's packed on a few pounds. And he puts those same shorts on, and that elastic band is stretched to its limit. Well, let's talk about that. before he put the shorts on, the elastic band was the exact same length for all 3 examples. In the first one, there was no change in the elastic band. It fit perfectly. In the fall example, he stretched that elastic band some amount. There was a delta. And in the winter, he stretched it more, so there was lots of delta. So all 3 of them had the same original length, but they all had a different delta. One had 0, so the delta is 0 divided by the original length, no strain. Some delta divided by the original length, some strain. Lots of delta divided by the original length, lots of strain. So it's something you intuitively understand, and it throws you off when you talk about big objects and unitless measurement, but intuitively you do understand strain, and that we're talking about how much something has deformed. Okay, so now we're going to do some math examples for this. Let's take that same 25 millimeter cube that we talked about before, and we want to know how much strain would be on it if it deformed 1 millimeter. So let's take a look at what that means. We have our this was 25 by 25, and what we care about right now is this height of 25 millimeters. And something's happened, and the change in length, whether it's squashed or stretched, we don't know. We just know that there is a delta L of 1 millimeter, and we want to know what the strain is. We know strain equals delta L divided by L. So we have 1 millimeter divided by 25 millimeters. So 1 divided by 25 equals 0.04. Now it's unitless, but sometimes I find it helpful to write that down. I just want to do a quick thought experiment with you. We had this, so it didn't matter if this was in tension or compression. Let's take a look, let's see what happens if we use the final length. So, final length. We have our delta L is still 1 millimeter. Let's take a look at it if it was in compression. So if we had squashed this 1 millimeter, this would be 24 millimeters now. So this is not the right calculation. I just want to show you why using the original length is important. The quirky thing is that the values are very, very similar. Let's see here, 1 divided by 24, 0.04167. Let's see if we had stretched it instead, so that now our final length is 26 millimeters. 1 divided by 26, 0.03846. So this is the strain we use. This is what we talk about. People often ask, why don't we use the final length? Now, the final length, it doesn't actually change our values that much, and you're going to see when we talk about actual buildings that the deformations are very, 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 very small, and so it doesn't actually matter that much if we use the original or final. But the thing that has the most telling impact is that if it's tension versus compression, it has a doubling impact of what the difference is. So with this version, it doesn't matter if it's in tension or compression, our strain remains the same. That's the amount it would move dependent on the energy that's applied to make it move. It makes a difference whether it's in tension or compression. So, a long time ago, everyone said, let's make sure we use the original length to analyze these calculations. You're going to do one in the assignment where what I want you to see is not talking about the difference between tension and compression, but just how little the difference is between original and final length when we're talking about these kind of large-scale object calculations. Just to give you a sense of how small these movements are. Okay, so why would we bother switching between force and stress and deformation and strain? Why would we bother with that? We get it, you've explained it to us, but why would we need to do that? Well, some of it is because structures tend to be really hard to test, and we need a way to think about these things on a smaller scale. So all of these things are obvious, but buildings are very large and very stiff. So if I drew you this building unloaded and applied a bunch of load and showed you it deformed, you wouldn't be able to visibly see the difference very easily. We're talking about millimeters of deformation on something that is very, very, very large. Those millimeters matter a lot, but it's really hard to actually measure. I know, you're gonna find clients that can pick up the slightest fraction of a millimeter of movement, but when it comes to actually measuring buildings, it's very difficult. So we need to be able to break things down at a small scale and work with them, and then go back to the bigger object. So the part behaves like the whole, is what we're really saying. We take this small unit element of material, figure out what's happening on the whole object, talk about it on the small object, figure out what we need, and then we can pick what big object we need. Or we can go about it the other way. And this is important because now we can test small elements of things to figure out how these materials behave. So it's really hard to test our full-scale elements. If we know the part behaves like the whole, we only need to test little elements to understand the material. So, we do that exactly for our different materials. Steel, for example, will test a coupon or a dog bone, and it's literally a little piece that looks like this, and you're actually going to see a test that they do this. We apply a load, whether we squash it or stretch it, measure the deformation, and measure the load at failure. And then we can come up with some correlation with how this material behaves, and then we can extrapolate it to big overall elements. So there are always exceptions to the rules to these things. These stresses and strains that I'm talking about, they make sense for buildings, which is 99.999% of the applications we're going to be talking about. Where these things don't make sense anymore is when we're talking about phase change, but we're not talking about vaporizing our steel very often. Extreme temperatures, and extreme stresses and strains. So a phase change, though, that it might be applicable would be an ice hotel as it evaporates or sublimates away. Extreme temperatures. Steel in a fire actually is a really good example. In extreme high temperatures, steel does not behave the same as it does in our normal everyday temperatures. So in extreme fire, steel will lose its strength. And so we actually have, knowing that's important because now we protect steel from fire when we need to. Extreme stresses and strains, just as a ridiculous example, a black hole, but I don't think any of us are building a building near the edge of a black hole anytime soon, so I think we're safe from that one. Here's where it gets cool. There is a direct relationship between stress and strain that is very helpful for us, especially when material is in its kind of normal easy zone. And we're going to draw this and talk about what it means. The relationship between stress and strain is stress divided by strain, and we refer to this as the modulus of elasticity. The modulus of elasticity is the measure of the stiffness of a material, and like I said, it is stress divided by strain. So modulus of elasticity, big capital E, and depending on the material, we might even give it a fancy name. Like for steel, we talk about the Young's modulus. So stress divided by strain. Remember, our stress is in MPa, which is newtons per millimeter squared, divided by strain, which is unitless, millimeters per millimeter. So that means E is MPa as well, or newtons per millimeter squared. Dividing out by the strain is not changing our units. So what does that mean for us? We know that modulus of elasticity is stress divided by strain. But look, we have stress is force divided by area, and strain is the change in length divided by the original length. Well, what if we plot this in here and this in here? The modulus of elasticity is equal to the force divided by the area divided by the change in length divided by length. That's clunky and bulky. Let's just rearrange some of those. Aha! Modulus of elasticity is equal to PL divided by delta LA. This starts to be very, very helpful for us. If we know the force that's on it and the length that's on it, we could possibly, and we know what the material modulus is, and we know what area we're talking about, we could figure out how much it deforms. Or we could rearrange this in other ways. So, knowing length and area, we could calculate the force or the deformation. For common building materials, we know the stress and strain from normal ranges because we take those little pieces and we test them again and again and again and again and get a good idea of how that material behaves. And if we do that enough, we can confidently say that we know what E is. And so if we know what E is, now all of a sudden we have a bunch of different things we can calculate. Because we as the designers are saying, will this element work to support this load? So we're picking an element and then calculating to see if it works to support that load. So these are all the different ways we can rearrange that formula. We know for a bunch of different materials there are some common modulus of elasticities that have been calculated on our behalf by a bunch of people again and again and again. Structural steel, 200,000 MPa. It's the only one I need you to know. I want you to memorize it. Say it out loud, if you will. Modulus of elasticity for steel is 200,000 MPa. Often, I actually make everyone chant it in the class, and you all find me super annoying, but it is the one I want you to know. Modulus of elasticity for steel is 200,000 MPa. That's going to be handy because it lets us quickly compare other materials. If we know one of them and hold one of them in our head, we can talk about things rather easily. Look at concrete. Now, this is a very broad, the modulus of elasticity for concrete is tied directly to its strength. So this is just an example. Wood has a wide variety, so this is just one example as well. But look at how low they are compared to the modulus of elasticity of steel. Steel is very stiff. So let's do a few examples with this to help us get our head around it. Okay, let's take a look at that cube that deformed 1 millimeter. What was the force on the cube? Let's see what force that cube saw. So we have our 1 millimeter by 1 millimeter cube, and we want to know what the force is on it. Sorry, let me just... Okay, so we have an original length of 25 millimeters. We have a delta L of 1 millimeter, We know we have an area of 25 by 25 millimeters, or 625 millimeters squared. And they have said that this was steel, so we know that the modulus of elasticity is 200,000 MPa. So we know the original length, the change in length, the area, and the E. That means we can figure out what P is. We know that E equals PL divided by delta L A. We want to rearrange this to find P. P equals E delta L A divided by L, or P equals 200,000 MPa times 1 millimeter, I'm not going to put the units in, times 1 times 625 millimeters squared, divided by our original length, which was 25 millimeters. The force, so 200,000 times 1 times 625. What am I writing here? That's 25. Sorry, guys. Divided by 25 equals 5 million. But it's 5 million newtons, so this is the important thing. My writing is horrible today. So 5 million newtons, we like to talk about things in kilonewtons. So that's 5,000 kilonewtons. Now, wait a second. If we came back up to this, it said that the maximum force this cube could see was 218.75 kilonewtons. This force is greater than what our cube could take. We can't have 1 millimeter of movement. We would have failed it. So this was a theoretical exercise where we wanted to know if we moved it 1 millimeter, what force would be on it. But it doesn't look like we can move it 1 millimeter because we've exceeded the amount of stress that we could have put on this thing. We know that this was the maximum force that we could see because that was the maximum stress they told us we were allowed to have on this cube. So this couldn't possibly be right. So this won't work. I wonder how much would it move with the 218 kilonewtons on it. Let's see what that would be. So we have our cube, and we know that the stress max is 350 MPa, and we figured out the area. So we know that this directly relates to a maximum force of 218.75 kilonewtons. E equals PL delta LA. We want to know how much this will move. So let's rearrange our formula. We're going to get delta L equals PL EA. We know our force, we know our original length, we know E, we know our area. Delta L equals 218,750 newtons. I've converted my kilonewtons back into newtons. I didn't write it out. I did it all in one step. Times our length, which is 25 millimeters, divided by 200,000 MPa, which is what we know the E is for steel, and our area, which is 625. 218,750 times 25 divided by 200,000 divided by 625, we're only going to get so our blob of steel that is very tiny can experience up to a very large force, and that very large force barely deforms our object. This is why we need to work with smaller objects. It's very hard to measure these things. We can do it mathematically, which is what we need to be able to do. But how can we prove these things? We need to be able to test small objects. That takes a huge amount of force to be able to move this a very small amount. Let's do another one with a blob of rubber instead. So if we said that that same cube of 25 by 25 by 25 has an E of 55 MPa, how much load does it take to deform it 1 millimeter? So we know its original length is 25 millimeters, and we know its area is 625 millimeters squared. We know that P equals E delta L A divided by L. We just figured that out in the last example. So P is, 55 MPa, so not 200,000 MPa, but 55 MPa times 1 millimeter times 625 divided by 25. 55 times 1 times 625 divided by 25, we get 1,375 newtons. Oh, guys, sorry, here we are. So, E is 55 MPa, so much smaller than our 200,000, MPa. We have 1 millimeter of deformation. Our original length was 25 millimeters, and our area is 625. We calculate this out, but our answer is in newtons because we were talking about things in newtons per millimeter squared. So P equals 1.375 kilonewtons. So to take this 1 inch by 1 inch by 1 inch blob of rubber and deform it 1 millimeter, it takes 1.375 kilonewtons, or about 1.375 Arnolds, or around 309 pounds. That is something we can get our head around a little bit, because it is a less stiff material. When I say it's less stiff, it means it has a lower modulus of elasticity, or less force will cause it to deform the same amount. So these are all terms that you do know. It's just that we're trying to take them and apply them to things that are very stiff and very big, which makes it hard to talk about a little bit. And that's why we need to be able to do it with math instead, because it allows us to talk about these very large, very stiff objects. So what we've done with materials is we have taken a series of these small samples and we test them. We start at the beginning and we apply a little bit of load and see how much it deforms, and then we'll maybe unload it, or maybe we'll just keep loading it in increments, and we track what happens as we do it. And we've developed this relationship called E. but I'll show you how that actually draws out on a diagram. And we do it beyond that. We keep testing it all the way until it fails to see what happens. And we can tell a lot about a material by that diagram. We call that diagram a stress-strain curve. And you'll hear some people refer to it as a force deformation diagram, which really means they know what the area it is it's been applied to, and they know what the cross-sectional area, of the material is, and they know its original length. And so they'll be talking about the change in length and the actual load being applied. We will often talk about it as a stress-strain diagram, though, because that means we can take it and extrapolate it to another test as well. And you've seen me talk about these for earthquakes, where we test them, we load it and unload it and load it in the opposite direction. When we do that again and again and again, these stress-strain curves actually become a hysteresis. We're not going to worry about hysteresis right now. We're just going to talk about our stress-strain curve. So we can start to tell a lot of things about a material by looking at its stress-strain curve. Now, the part that we care about, because we're talking about structural engineering, is rather boring. This is what a typical stress-strain curve for the portion that we're going to need for our calculations looks like. We plot the stress here and the strain here. Notice I put MPa, and this is unitless. And we know that if there's this much stress on it, there's this much strain on it. If there's this much stress on it, there's this much strain on it. And E is stress divided by strain, or the slope of this line. And that is, for the most part, most of what we need. You're going to need to be able to recognize a full stress-strain curve of a couple other things, but you're not going to need that much more information out of it. I'm going to talk to you about them, and I'm going to show you a lot of interesting things about them. But I'll be very clear about what you need to know. Useful terms you should know. Sorry. I needed some sugar. Okay, elasticity. Elasticity is the tendency of a material, when unloaded, to revert back to its original shape in the manner to which it became deformed. That means we take that object, we put a load on it, there's deformation, but if we take the load off, it goes back to its original shape. Plasticity is when we have deformation that is permanent, or deformation of a material undergoing non-reversible changes of shape in response to applied forces. We load our object, but when we unload it, it does not go back to its original form. That means there has been plastic deformation. Yield stress, the point at which a material transitions from elastic behavior to plastic behavior. After this point, some portion of the deformation will be permanent. Not all materials have a yield stress, because not all materials have a plastic zone. In fact, you know what? I'm going to add that right there into the slide. Plastic. Not all. Ductile. A material which will undergo large permanent deformations, thereby absorbing a great deal of energy before failure, is called ductile. A material which is not is brittle. So if we have lots of permanent deformation, but the object hasn't failed yet, that is what we call ductility. So we apply a load, there's lots of permanent deformation, but it doesn't necessarily fail right away. If it fails right away, after we switch from elastic, if we hit the end of the elastic zone and it fails, that means it's a brittle material. Ultimate stress is the maximum stress that a material can sustain. Or whether if it is a brittle material, we load it up to the end of the elastic zone, and its ultimate stress is when it hits the end of the elastic zone and it fails. A ductile material, or one with a plastic zone, will experience load and have large-scale deformation up to a point, and then there will be a stress where it actually fails. There are some other terms that you don't necessarily need to know for this. You should recognize them. I'd like you to be comfortable hearing them from me. But don't worry about these ones too much. The proportional limit is the maximum stress at which the material behaves in a linear elastic manner. Strain hardening, an increase in the stiffness of a material as the stress increases. That is not a common behavior, but it does show up in some materials. Strain softening, the exact opposite, a decrease in the stiffness of a material as the stress increases. So again, not all materials. The elastic limit. The elastic limit, the maximum stress that a material can sustain without undergoing permanent deformations. So when we switch from the elastic zone to the plastic zone is the elastic limit. Remember, after that, we would experience permanent deformation in our material if we unloaded it. Fracture strain is the strain at which fracture occurs. Strain energy. Strain energy is the amount of work done in deforming an object from its original shape. It is the area under the stress-strain curve. The elastic strain energy, or the modulus of resilience, this is the portion of the strain energy which is stored as potential energy and is re-released in springing the object back to shape. Plastic strain energy is the amount of that strain energy which is absorbed by the object undergoing permanent deformation. Now, one of the things I like to use to illustrate this is an everyday paper clip. So if we have a paper clip and we lift it just a tiny little bit to put some paper in under there, I'm using my nail, I'm putting my nail under there. When I take my nail out, it goes back to its original shape. No problem. Lift it up, and you can almost feel where it's happening. I let go, it goes back to its original shape. But look, if I put a lot of paper in there, when I let go, there is permanent deformation. But did you see? Look how much it's deformed. When I let go, it doesn't go all the way back to its original shape, but it does have some reversal of shape. So we had gone into the plastic zone, and when I released it, we had our elastic strain energy, or the stored potential energy, that reverted it back to its original shape. But then some of it was plastic strain energy that was absorbed by the material because we underwent permanent deformation. And we can do more of that. We can do it again and again. So we can stretch it more. And look, it doesn't matter. I will always have some elastic resilience or some modulus of resilience popping it back into place. But if you did this, if you held right here, if we had very sensitive probes, you'd feel heat right there. We are taking that energy in the plastic strain and turning it into something. In this case, one of the things is heat. So we're absorbing energy there. Now, we can keep doing this, and modulus of toughness is the total strain energy at rupture. We can keep manipulating this, and eventually we will have our final failure. So we went through the elastic zone, in where we would have a reversal of load. We went into the plastic zone where we had some reversal of shape, but not all the way back to its original shape. And then we had large scale permanent deformation or ductility action happening. And then we went all the way to the end where we had rupture with a very large strain on the object. And all of that is our modulus of toughness. So let's take a look at some of these. All the words are fine, but let's take a look at these diagrams. And I'm not too hung up on all of those definitions. What I really care about is the diagram, and you should be able to see some of these things on the diagram. So concrete, what do you think? Do you think concrete is ductile or brittle? Remember, that's that ability to have large-scale deformation without total failure. Well, concrete is brittle. When we hit the end of our elastic zone, we fail concrete. Now, you're probably thinking, concrete doesn't deform. It can't revert back to its original shape. It seems that way because we're used to associating so much of that stuff with ductile materials or something with a plastic zone. But concrete can take a load and revert back to its original shape. It's hard to notice, it's hard to measure because, again, these things are hard to notice on a large scale object. But that zone is there. There is an elastic zone in concrete. So this might be an example of a concrete stress strain curve. Now this one is in compression. I'm even going to note that the concrete stress strain curve is compression, because concrete in tension basically is zero. It does not have the ability to take pretty much any tensile force. So this is our stress strain curve in concrete. It's only an elastic zone. That is our modulus of elasticity on this particular piece of concrete. The modulus of elasticity varies depending on the concrete mix, and it's tied to a few other things. You're not going to need to be able to calculate that. That is a thing I would always give you for concrete going forward in our concrete modules. So here's a modulus of elasticity for this concrete, which is the stress divided by the strain at various points. And it's a linear relationship. There is our ultimate stress and our ultimate strain. We have an elastic zone, but no plastic zone. Our object is brittle. With no plastic zone, we are saying there is no ductility, therefore our material is brittle. Let's look at the stress strain curve of steel. I'm going to start with a very close-up zoom of the steel stress strain curve, because that is where we tend to keep our analysis. This is the zone where we do most of our math. You're still going to need to be able to recognize the look of an overall steel stress strain curve because it's very handy to know. So we've got stress on this side, unitless strain down here, and here is a stress strain curve for steel. There's our modulus of elasticity, E, or stress divided by strain. There is our yield stress. So at this point, we would stop seeing a reversal of shape if we unloaded the object. We would start to experience permanent deformation at this stress. This is our proportional limit, where our stress strain curve E stops being totally linear. Elastic zone, plastic zone. So let's take a look at what happens to our object when we load it and unload it. If we load this red line is our load. If we load it up to this stress, so we've taken it all the way to here, we've had deformation because here's our strain, and if we unload it, everything goes back to looking like normal. Our object would come right back to here, no load, no strain. If we load it, that right there is our elastic strain energy, or the potential energy that's held in the object so that when we let go or release that load, it will revert back to its original shape. So for that period of time, it's holding some energy. There's some potential energy there that we let go and it reverts, or unload it, and it reverts back to its original shape. If we start to go into the plastic zone, however, we load our object up to this stress. When we unload it, we come back down to zero stress. But look, we have some permanent amount of strain in this. There is permanent deformation in that object. So we now have permanent strain, but no stress, even though we have no load on the object, but there is residual strain. When it was loaded, this area under the curve was the elastic strain energy, ready to go back to its original shape. And this was the plastic strain energy, the energy that was permanently absorbed and converted into some other form of energy while it was loaded. So this is the total area under the curve. This was our the energy that was absorbed or converted. This was the potential energy that when we let go was able to revert our object back to its original shape. Not to its original shape, but almost its original shape. That amount of strain there is what we call residual strain. So that's the residual strain of having gone into the plastic zone. This line, this slope, will follow the same slope as our modulus of elasticity. We can load it again and again. If we've loaded it up to this point here, we have elastic strain energy here, and this zone becomes our plastic strain energy, or the amount of energy that was absorbed by the material and converted into some other form of energy. You can see that the further we go into the plastic zone, the more energy is absorbed by the material. You can imagine that could be a very handy thing if we were talking about earthquakes, if the building can actually take that energy and convert it into something else. We can stop it just from being a force, straight force applied to our object. We can actually absorb the energy. So that was just a small portion of our steel stress strain curve. The steel stress strain curve is actually much larger than that. That is the portion we've talked about already. This is the full stress strain curve. Now, I said there were some terms you don't need to worry about, like strain hardening. Those are things that happen to steel, the type of steel we tend to work with, but there's different mixes of steels. But the steel we tend to use structurally experiences something called strain hardening, where as we strain it, we actually get some small increase in the ability to take more load. Not all materials experience that. It's not something we're going to do a lot with in our course, but it is handy because it tells us what our ultimate stress is. Here's our yield stress, but look, the total stress we can actually take is a little bit higher, and that might be handy for certain things. So, yield stress, ultimate stress, strain at rupture, so this is when our material finally broke apart. If we loaded the object up to here, so we've put this much force on it and we've experienced this much strain, if we unload it, we will come back down to here. This is our residual strain. This was the plastic strain energy, or the amount of energy that was absorbed and converted in the deformation of our object. And this is what was held when we were at this point as elastic strain energy and allowed us to convert back to this shape. Not our original shape, but we did move back some amount when we unloaded it. So zero stress down here, but quite a bit of strain. The entire area under this curve, all the way at failure, is modulus of toughness. This is the definition of how tough it is, or the final amount of all energy it took to make this thing fail. So you should be able to recognize this right here. In fact, this would probably make a sweet exam question right here. Maybe something with matching, I don't know. So some common yield and ultimate stresses. So steel, the yield stress is 350 or 345 MPa. I'll talk about why it's 350 or 345 in our steel modules. And the ultimate stress is 450. Stainless steel, 215 is our yield stress, and our ultimate stress is 505. So look at this. Stainless steel yields at a much lower stress, but its ultimate stress is much higher. Aluminum, very low yield stress and a very low ultimate stress. Now look at brass, concrete, and wood. They have no yield stress. What does that mean to you? That means that they are brittle materials. There is no point at which they will yield. They hit the end of their stress-strain curve linear portion, and they fail. They do not have any yielding. There is no plastic zone. There is no ductility. When they hit the end of that flat slope of the stress-strain curve, or that linear relationship, they will fail. So these would be the worst stresses that we could allow in our material without failing. So if we say, you know, what we want to limit to is the yield stress for yielding materials and maybe ultimate stress for some other materials. If we say that this is the worst that we ever want to see before it yields, and we'll save yielding for something else, past that for something else, we have a limit on what we want our material to see. So if we knew a cross-sectional area, for example, of a particular member, we could calculate how much force that material could see. Because remember, stress equals force divided by area. So if we knew the area and we said that this was the maximum stress we wanted our object to see, we could figure out the maximum force that exact member would be allowed to see. Kind of seems like it's heading into the direction we want of our capacity. That sounds like it would be the capacity of our specific member. We have to figure out the reduced capacity, because remember, we want the reduced capacity to be greater than the factored load. And it sounds like now we're starting to get somewhere on capacity. So let's watch a little video. Oh, that wasn't very smart of me. Let me pull this out, and we might as well, let me see if I can do it with my weirdly massive mouse cursor. I will, sorry guys, I will escape from this. Let's go to this. Alrighty.
The tensile test. First test, material with yield point phenomenon.
This is not going to help you guys. You need it over on the other screen, because this is not what you were seeing. You need this over here. Alright. So, we are going to go through two different tests.
In the first tensile test, a plain carbon steel with yield point phenomenon is to be tested.
Every year, but that
This is the test piece. It has a cylindrical test region with an original diameter of 10 millimeters and an original gauge length of 100 millimeters.
Okay, original length, original diameter, and we know diameter is directly related to cross-sectional area for a circle.
They help to visualize and measure the plastic behavior of the specimen.
They've marked it just to kind of help you
Using
know
hand
how it's
control,
measured.
the tester moves the upper crosshead into its correct starting position. Now he can place the threaded ends of the test piece in the lower and upper grips of the testing machine. In the next step, he swings the extensometer into its working position and checks that everything is correctly prepared. Then he selects all necessary testing parameters on the control computer. Ready. The test starts, and the extensometer's sensor arms are carefully pressed onto the test piece.
So this is our
This
dog
way,
bone
the
sample
gauge length can be measured throughout the whole tensile test.
that they're going to apply
The
load
gauge length is displayed at the bottom right-hand corner of the screen.
to measure how much it
At the
deforms,
beginning, it amounts
but
to
they have the
100
length.
millimeters.
And then the
During the
cross-sectional
tensile
area.
test, the test piece is slowly and constantly elongated with a
force.
standardized speed. The force
But we know
that
the
the
area.
test piece opposes to the imposed elongation is recorded and can be seen at the bottom left-hand corner of the computer
They make
display.
it so confusing.
The material behavior can
Here's how
best
much
be
it
observed
moves.
in a force elongation diagram.
Force
The
elongation.
force F
we can,
is being plotted
we
upwards
can
on the
convert that to
vertical
stress,
axis.
and we can
The
convert that to
elongation
strain
delta
very
L
easily.
towards the right on the horizontal axis.
Okay,
At first,
so they're
the
applying
force
load.
rises rapidly. Force and elongation are proportional and form a steep, straight line in the diagram.
Modulus
In this area, the material behaves elastically.
elastic zone.
If the test piece were to be unloaded from this area, it would spring back completely to its original length.
No residual strain.
In materials with yield point phenomenon, the end of the elastic area can be seen clearly. the plastic deformation starts abruptly and is accompanied by a sudden drop of force. If the test piece were to be unloaded now, it would not spring back to the original length, but instead show a permanent elongation.
There'll be residual strain.
In the next stage of the tensile test, an almost constant force level with slight fluctuations occurs. This phenomenon is called the Modulus effect.
We don't worry about that. It is the plastic zone.
After a certain strain, known as the Modulus strain, the force increases again.
Hardening.
The material opposes an increasing force against
You don't have
the
to worry about
membrane's
strain
elongation.
hardening.
It strain hardens.
But you can see that we're starting to be able to take
Up to the
more
point of
stress
maximum
again.
force, the test piece is strained uniformly along its length. This means that the test piece
can
gets longer and
see it's
thinner, but
stretching.
keeps
Look
a
at that.
cylindrical shape. As soon as the maximum force is reached, a neck begins to form at one point of the test piece.
It starts
All
to
further plastic
now it's gonna
deformation
have
now only takes
smaller
place at the neck,
cross-sectional area
and
at
eventually
that
the
zone.
test piece fractures there.
see now all the deformation. It's not uniformly happening across its length now. It's only happening here. So now we're pretty darn close to failure. There we go. So, modulus of elasticity, yield, ultimate, strain at rupture, force, which we can convert to stress.
In the recorded
strain,
force
which we can
elongation
convert to
diagram, the
support.
force FEH at the upper yield point can
I just want
clearly
you
be
to hear
seen.
them, that I'm
This
trying
is
to
the
make it
highest
better.
force the test piece can sustain elastically. FEL is defined as the force at the lower yield point, Fmax as the maximum force. Using these forces, the strength properties of materials can be calculated.
Stress.
The upper yield strength REH is calculated by dividing the force FEH by the original cross-sectional area S0. The lower yield strength REL is defined in a similar way. The maximum force divided by the original cross-sectional area is called tensile strength Rm.
Don't worry about those.
In the last step, the tester swings the extensometer back into its resting position and removes the broken test
So
piece.
you guys remember those failed pieces of steel that I showed you in the first lecture of Structures 1
On the
and
work
Structures
table,
2?
he puts the fragments back together again. With the help of the distance marks, the percentage elongation after fracture can be determined.
How much is deformed?
This
If
is
they
the
put
permanent
an
strain
original,
after fracture and
here
amounts
was
to
the
about
equivalent,
30% in this example. Please
original
note
example.
that the percentage elongation after fracture depends on the length to diameter ratio.
So the diameter is
By measuring the
related
smallest diameter
to,
at the point of fracture,
the
the
deformation.
percentage reduction of area can be calculated. It describes the reduction of
Don't worry
cross-sectional
about this.
area at
We're
the
not
point of
worried
fracture
about
in relation to
netting.
the original cross-sectional area.
That's
In the second
handy if you're
tensile
into
test,
deeper
material
things,
without
and we
yield
use
point
it for other
phenomenon is to be
calculations, but
tested.
that's way beyond what we're doing in this course. Now
In
we're going
this
to show
case, it is
another
a
material, just to
precipitation
see that not all
aluminium
material has
alloy.
the exact same stress
The
strain
test
curve. So this
piece
is
has
a
exactly
different
the same shape and
material.
dimensions as the specimen in the first test.
coupon is exact
It is
same.
cylindrical, with an original diameter of 10 millimeters and an original gauge length of 100 millimeters. After fitting the test piece into the testing machine and panning the extensometer into its working position, the test can start.
Okay, so here we go again. We're testing a new one.
The initial linear
Force,
curve in the force
deformation.
elongation diagram again shows the elastic behavior of the material. But this time, the end of the elastic area is not revealed by a sudden drop of force or any distinct change. There is a smooth and gradual transition from linear elastic behavior to plastic deformation.
Elastic zone, plastic zone.
In the further course of
Linear
the
slope,
tensile test, the force
modulus of
increases
elasticity.
and the test piece again is strained uniformly along its length. At the point of maximum force, a neck develops, and all subsequent plastic deformation is confined to this neck until fracture finally occurs there.
So you can see we have all the same things. We have a yield stress, an ultimate stress, the strain at
As a common
rupture,
substitute for yield
stress
strength,
on this line,
the
which is just
0.2%
force divided
proof
by
strength
area,
is used.
and strain, which is
It
the
is the
delta L
stress that
divided by the
causes
original L. Both
8.2%
things
of
they
plastic
knew already.
deformation in the material. And this is the way to calculate it.
So
First
we're not
of
going to
all,
worry
the elongation
about
that corresponds to
strain
0.2% of
elongation.
strain
So
has to be computed.
that's beyond what we need to worry about in this. Trying to look at the wrong screen. Okay. So let's go back to our, I have to switch some stuff around, swap screens, minimize this. Okay. So I just wanted to show you that so that you can see some other examples of stress strain curves and really what information we can get out of it. And also that I'm not a total kook and the things I'm telling you aren't completely out to lunch, that this is a system and a method that's been done again and again and again and again, and engineers around the world talk about it in the same way. Mostly the same way. Some of you heard her talking about it in a slightly different way, but the information was all the same. She was talking about it at a higher level in some ways, but there wasn't actually that much more information in hers. She was more picky about kind of what was happening right here at this, but we're not worried about that too much. You know, we have our yield stress and our ultimate stress are the things we're going to be worried about. But mostly what we want to do is stick it out in this zone right here. This is the zone that we like to work in as structural engineers. So, okay, I just wanted to see where I was going with that because I didn't think I had this slide in this one. Okay, so shear is it's the force that causes racking in our objects. So, you know, it's what's happening on this singular plane, but then there's the plane right beside it and the plane right beside it. And if you start to look at those, as we start to slip these two things past each other, this side going down and this side going up actually deforms our shape to look like this. It is similar to these two corners being squashed together and these two corners being stretched out. Now, this is not something that you need to know. This is not something that I'm making you analyze. I'm just talking about it so that, first off, there's always some people in the class that are really interested by these things. So I just want to give you at least a little bit of information on it. And we're going to use some things later on in the term that you're going to be like, where the hell did this come from, Shannon? And some of it comes from the derivation of the stress information. It's beyond what we're going to analyze in this course, but I wanted to show it to you as a talking point. So this stress is very similar to equal and opposite loads acting on an element oriented at 45 degrees to the shear axes. So shear axes, 45 degrees, compression, and stress, or tension. So shear and its equations, again, don't worry about these. The treatment of shear is analogous to that for axial loads. So our shear stress is our shear divided by our area. Our shear strain is our basically change in skew angle. And G, or the modulus of rigidity, or shearing modulus of elasticity, is our shear stress divided by our shear strain. That sounds very similar to our axial loads. Our stresses are similar, our strains are similar, and the modulus we talk about is similar. This one is an angular one, so if we go back to look at that, it's actually talking about what the skew angle is. But again, this is beyond the course. The reason I want to bring it up is this term G gets used in steel analysis. And we're going to do this big equation, and the equation, and in it is G. And we know what it is for steel because it's related to E. But I wanted you to at least know that I just didn't make G up. It comes from something, and it comes from everything we're going to do in axial loads and everything we're going to do in bending loads. We're not going to do in shear, but it's very similar to axial, and G comes out of that process. The relationship between G and E looks like this. Again, this is not something you need to know. I am not making you know this, but I just wanted to talk about it so that you can understand that it exists. So G is equal to E divided by 2 times 1 plus V. Now V is the Poisson's ratio. The Poisson's ratio is, if you want to call it the bulging effect, is a kind of a good way to talk about it. When we were talking about our deformation, we just talked about the change in length, about how much it's squashed. We ignored the fact that that material goes somewhere. It doesn't just disappear. It pops out on the sides. We didn't worry about that at all. We were just talking about that change in length. Well, the Poisson's ratio is talking about how much it actually bulges when it squashes down. It's, again, beyond this course, but that bulging ratio is tied to its shear strength, or that skew angle, and that is then related to the modulus of elasticity. So we can tie all of those things together to figure out what V is, which lets us figure out what G is, based on what E is, which is the only one I'm going to make you worry about, but we use them in our steel analysis. So they're just terms I want you to hear because we're going to use them. I can tell you that I spent a whole term just working on Poisson's ratio for different materials. You guys are hearing about it once in about a 30-second blurb. So here it is. It's really talking about, you know, that's our change in length that we talked about with strain, and then we have how much does it bulge relative to its original non-bulged shape. So here's our recap. Here's our very handy, useful set of things based on our very basic principle of stress and strain. We know, if we know what element we're talking about, we know how long it is originally, we know what its cross-sectional area is originally. If we know how much load is being put on it, we can figure out what that stress is, and we can figure out how much it's going to deform. If we know that we have a limit on how much stress it can see, well, we could say if it works or not. If we know there's a limit on how much it can deform, we can say if it works or not now. So force equals E delta LA divided by L. We can rearrange that for area, we can rearrange that for deformation, we can rearrange that for length. All based on our stress, our strain, and our modulus of elasticity. So with all of that, we now have the ability to figure out the capacity and the deformation of elements, which is really what we need to do. We need that reduced capacity to be greater than that factored load, and we need to make sure the actual deformation is not greater than the allowable deformation to meet our stiffness, or so the first one was for strength, the second one is for stiffness criteria. So let's do a few quick examples now, just to kind of really lock it into our head. Okay, let's do one last example that kind of ties in all the things that we've talked about today. We have a column that is 3.2 meters tall. We know that there's a factored load of 5,000 kilonewtons being applied to it. They have told us that the width is 50 millimeters. It needs to fit in a very particular space. But depth is the thing we need to determine. So this is a cross-section in plan. One side is 50 millimeters and one side we don't know. We want to figure out what that needs to be. If the maximum deflection can only be 5 millimeters, and our maximum reduced capacity of steel is 270 MPa. Look, they've put that on there to let us know what we're talking about. They are using a factored load. We're going to go with that for right now. We're not going to revise that to be a serviceability load, but we're going to go through these calculations to figure out what the required depth is here. So I always like to start out by writing out everything I already know. So, given. So these are all the things I know. I know that the force is 5,000 kilonewtons. Let's make this bigger for you guys. I know that the force is 5,000 kilonewtons. I'm just going to convert this right now to newtons because I know we're going to be going back and forth between kilonewtons and newtons. So, 5 million newtons. The height, which is the original length of this, is 3.2 meters. Again, we like to be converting back and forth between meters and millimeters because we're going to be talking about stress in here. And once we're bringing stress into it, we know we'll be able to need millimeters. So 3,200 millimeters is our original length. We know that our width is 50 millimeters. They gave us that dimension. They've told us that Fy, now Fy is another way of writing stress. And I'm going to tell you, writing a Greek letter all the time is a huge pain in the butt. So often, especially when you're typing things and using computers, they have, for different materials, given that maximum stress, something could be a shorthand. So they have given us a reduced capacity of 270 MPa for steel. Fy is another way of writing stress. Or in this case, the maximum stress. The maximum stress we could see for this. So this is a limit. We don't want to go over that. If we go over that, our object doesn't work. E, we know for steel, is 200,000 MPa. That's one of those things we all know now. And the delta max that we're allowed to see is 5 millimeters. If we deform or if we squash this more than 5 millimeters, we have failed our object. So we have two different criteria. We have a maximum stress and a maximum deflection. So what I would often do here is check, what D do we need for strength? What D do we need for stiffness? And then obviously we need to take the larger of those two, because if we take the smaller one, the other thing will fail. We want D required for strength and D required for stiffness. Now, I'm going to acknowledge right now that we're using a factored load for our stiffness calculation. I'm just trying to show you how the methodology works. This is why it's always so complicated to teach anything in this course, because as much as it's a very straightforward procedure, there are these other things that leave tiny little clauses. If I wanted to do this, I would have told you what the serviceability load was for this as well. But we're going to say that this particular example, we're using the strength load for some reason. So let's take a look at the strength. Let's take a look at strength, which we're really talking about stress here for axial. We know that stress equals force divided by area. We know that Fy is just another way of writing stress, and we know that we can rewrite that formula and we can rewrite this. What we really want is to figure out what area is. We really want to know area equals P divided by Fy. And we know that area is going to be B times D. Well, we already know B. So what we really want is D equals P divided by BFY. Now, we didn't have to rearrange this. We could have kept this and worked it out with the numbers embedded in that. There are multiple ways or different steps you can take to solve this. All of the steps will be done. You might have just done them in a slightly different order. This way, I can see easily that we already have P, we already know B, and we know what maximum stress we can see on this, which would give us the perfect D if we were trying to hit that stress exactly. Or 5 million newtons divided by 50B times 270 MPa. If we calculate this, we get 5 million divided by 50 divided by 270, we get 370.4 millimeters. So for strength to work on this, the depth of this needs to be at least 370.4 millimeters. So we need our object to be 370.4 millimeters at least. We need it to be at least that to work. Let's take a look at this if we were talking about strain, or our deformation. For our axial example here. We know that area equals PL E delta L. That's just one of the ways we've written out that equation before. We know that area is B times D, so what we're really looking for is D equals PL B E delta L. Well, it looks like we already know all of these things. P we know, the original length we know, B we know, E we know, and we know the maximum change in length we can possibly see. So we have 5 million times 3,200 divided by 50 divided by 200,000 divided by the 5 millimeters, which is the maximum we possibly want to see. We can plug all of that in. So 5 million times 3,200 divided by 50 divided by 200,000 divided by 5 gives us 320 millimeters. So to not deform, we need this to be at least 320 millimeters. So the question is, what size do we need? What is the size we need? Well, if we need for strength at least 370.4, and for axial we need at least 320, it seems like this is the one that governs, and for both of these criteria to work, we need a member that is 370.4 millimeters minimum. So D needs to be 370.4 millimeters min. Maybe they want to use 375 because it's a nice round number. that would satisfy both of these criteria. Picking 350 would satisfy our deformation criteria, but not our strength criteria. And we need to meet both of those things to work. So it's very important to check both of those. And if you want, you can see that worked out here again. So here it is, all worked out, matching all of the information I calculated right here. So I just wanted to wrap up the end of the lecture by saying what our takeaway tips were. So you should know generally, going forward, that stress and strain relate to strength and stiffness, and you should know that stress and strain are related. What you need to know for this course, you definitely need to know the equation for stress. You definitely need to know the equation for strain. You should know the equation for modulus of elasticity and all of the iterations of it, meaning plugging in stress and strain. And you should know the typical steel value for modulus of elasticity. It's the only one I'm going to make you memorize, 200,000 MPa. You should know what the steel stress strain curve looks like. I gave you a sweet hot tip on an exam question with that. And you should have an idea of elastic versus plastic. You should know what yield stress is. And by knowing elastic versus plastic, you should have an understanding of ductile versus brittle, because those are tied directly to that. So those are the things you're going to need to know going forward. We can now solve for the exact right object we need for axial calculations. We were able to say that this member will work for this load right here and these deformation criteria. So we are on our way to getting an answer. Now, this was already factored for us, and we know that, you know, we wouldn't have actually used the factored load in the deformation calculation. And we didn't actually apply our reduction factor. They gave us a reduced stress. So we know there are still some things we don't understand. And even more, there's that pesky thing that I have told you about before called buckling. And this didn't even think about buckling at all. So it seems like there's still more we need to learn. But generally, the basic premise of it for capacity, we now have. We've got it. Everything else is more just an expansion or broadening of this concept that we just figured out today, and that is the relationship between the equation for stress, the equation for strain, and then the relationship between stress and strain for modulus of elasticity. Everything going forward is just expanding on that. And then figuring out, like, what the heck this kind of weird buckling thing is. And that's it. That's all we have left to figure out. We also have to tie in that all materials are different, and some of them are organic, and some of them we mix in the back of a truck speeding down the highway. So it's probably a bit more complicated than that, but if you can get your head around this right now, you're going to be in really, really good shape for the rest of the term. Okay, so next week we move on to bending, and that's very exciting.